Hi, Susan.
Hey, Christina.
You want to keep talking about linear correlation and regression
I really
today?
do.
Yeah.
I do.
Yeah. Good. So this is in your 4.1 notes, and the first thing here is just some variables and some symbols. But let's talk about what our goal is here for a linear correlation and regression test.
Yes.
Yeah. So what we want to see is if there's a relationship between two variables that is good enough that we can use that relationship to make predictions, right? We want to look and see if there's a trend line that we can use to make predictions.
Okay. All right.
Okay. But for us to do that, we have to have a statistically significant linear correlation.
Which means maybe that our sample data points lined up in a pretty good line.
Yeah. Yeah. Exactly.
So that when StatCrunch creates this line of best fit, which is the best line for that data,
Yeah.
then we can use that line.
Yeah. Yeah.
To make predictions.
Exactly.
Okay.
Exactly. And so, the measurement that we use to decide how good that linear correlation is called the linear correlation coefficient.
Okay, and that kind of tells us how well the data points lined up in a line.
Yeah, exactly.
Okay.
So the parameter for that measurement is actually this Greek symbol here called rho, and it looks kind of like a P, but it is a Greek letter rho.
It is a Greek letter rho, like a lowercase r, actually.
Yeah.
In Greek lettering, and we've had other parameters, population parameters, that have had Greek symbols, like standard deviation had sigma, and mean had mu, and now we're looking at the correlation coefficient, and it has rho as its symbol. But that's for the population parameter. Do we have one for the sample?
Yeah, so our sample correlation coefficient is just called R. And actually in StatCrunch it has it as a capital R, but either way is fine to write down. But that parameter rho is what's going to be in our null and alternate hypotheses.
Because they're always about the population.
Right.
So therefore we would use rho.
Right.
Okay.
Right. So another important thing here is that correlation does not imply causation. You may have heard that before.
Right.
So sometimes we have a strong correlation just because of a coincidence. Right? There's a great website. Can we write the website down?
Yeah.
Yeah. It's called Spurious Correlations, if you want to look that up.
And there's just crazy things that they found that are correlated that really one of them did not cause the other one to happen.
Right, absolutely not. Like number of Nicolas Cage movies and like the number of drownings in a swimming pool or something like that. Yeah.
I think the problem that we're not going to work and that we're going to have them work has one of those.
Yeah, I think so too.
In it. Yeah.
Yeah. Sometimes there's just a common underlying variable that is affecting both variables, and sometimes there is a cause and effect relationship. But the point is that seeing if there's a linear correlation does not prove that one thing causes the other. It is just kind of a starting point to see if there's a relationship between the variables.
Yes. So if you don't walk away with anything else
the
whole semester, please walk away with correlation does not imply causation.
Right. Very important. Okay, so let's talk about the steps for our hypothesis test.
Okay.
So again, we've got that rho is your population parameter and R is your sample statistic. Okay. So the first thing that we're going to do, this is very much like the steps for our other hypothesis tests. We're just going to kind of lay them out specifically for the linear correlation test. Okay. So the first thing is to find your null and alternate hypotheses. These are always the same, okay? That linear correlation coefficient, the closer that is to 0, that means that there's less correlation. So our null hypothesis is that rho equals 0, meaning there's no correlation in the population, okay?
And that will always be your null hypothesis in a linear correlation test.
So that makes this always a two-tailed test.
Yes, because the alternate is not equal to,
right,
which is a two-tailed test.
Right. So that correlation coefficient is a number between -1 and 1, and the closer it is to -1 or +1.
Can we scroll down and look at that?
Yeah. I've got a picture down here. Yeah. Oh, well, there's this one, though. That's fine. So -1 is like a perfect negative linear relationship.
Which means all your points lined up in a perfect line with a negative slope.
Yes.
Not going to happen.
No, not with sample data.
No.
And then +1 is a perfect positive linear relationship.
Which means all your points lined up in a perfect line that had a positive slope.
Right. So as I get closer to those, I'm going to have critical values that will cut off that rejection area.
And those are R's.
And if I'm close enough to -1 or 1 for that correlation coefficient, that's how I know if I have a strong or statistically significant linear correlation.
Yes.
Yeah. So we'll come back to that.
Yeah. We're going to look at some pictures in a minute.
Yeah. So after you define your null and alternate hypothesis, you want to enter your data in 2 columns. Okay, you're going to have an X column and a Y column. And regardless of whether you're using StatCrunch or a calculator or Excel, you're always going to want to enter that data as columns. The only reason it's on rows is to save space on the paper.
That's it.
Yeah.
So in your homework and in your notes, you're going to see the X and the Y's listed in a row. You're going to type them into StatCrunch in a column.
Yep. And then you want to identify the following values. Okay, you're going to get your correlation coefficient R using technology, and again, that's a capital R in StatCrunch. We actually have to use a table
First time
to get our critical values.
Okay.
I wish StatCrunch would do that, but it just
I know
doesn't.
it doesn't.
It
So
doesn't have that
we're going to
option.
show you how to use the table.
Yeah.
Not a problem.
And then we can also get a p-value using
From
technology.
StatCrunch. Yeah.
Yep. Okay, so when we make our decision to either reject or fail to reject the null hypothesis, we can do that 2 different ways. Okay, there's 2 options.
Like always.
Like always. Yeah. We can always either use the p-value and compare it to alpha.
Yeah.
Or we can use the test statistic and compare it to the critical value.
Which in our case is the R, correlation coefficient. That's what we're using as our test statistic for this. Okay.
Yeah, and the reason we have this absolute value here, okay?
Oh, yeah, don't let that.
Yeah, that's just because your R value, your correlation coefficient for your sample will be positive or negative, depending on if the correlation is positive or negative. But in the table only has positive critical values listed.
Oh, so like down there where you just marked the R critical values, put a check mark beside the positive one. That's the one that we get.
Right.
And then we'd use the negative value that we know really exists because it's a 2-tailed test.
Right.
We'd just mark that down there.
Yeah.
Okay.
Yeah.
Okay.
Yep. And so if my p-value is less than my significance level alpha, or if the if the correlation coefficient is greater than the critical value, that means that I would be in the rejection region.
Since we're talking about absolute value of it, yeah, that means that it's further away from 0 than the critical values were.
Right.
And 0's right in the middle.
Yep.
Okay.
And if not, then I fail to reject the null hypothesis.
Okay, so in the tails, in the rejection region, reject the null.
Yep.
Otherwise, fail to reject the null. Got it.
Yeah, and then, so when I'm interpreting my results, if I reject the null hypothesis, remember that null hypothesis was that rho equals 0, which means no correlation. Okay, so if I reject the null hypothesis, then there is enough evidence to support a claim of linear correlation between my x and y variables.
Okay.
Okay.
I mean, it may not be a great correlation, but there's some, because the alternate is some correlation.
Right.
Not a great one necessarily, but some correlation is the alternate.
Yep. And if I fail to reject, then I don't have enough evidence to say that there is some correlation between my x and y variables. Okay? So in that case, we would say there is not a significant linear correlation.
Okay.
Okay.
So if I reject it, I have a significant linear correlation. If I fail to reject it, I do not have a significant, there's not enough evidence to support it.
Exactly.
Okay.
Yep. All right. And then the last thing that you may need to do is to use your conclusion, okay, to predict values. So
now, this is the first time that we're actually using our result from our test to answer a next question.
Right.
All right.
Yeah. So, if we rejected the null hypothesis, so we said that there is a significant correlation, all right, well, what that means is that regression equation, which is my line of best fit.
Oh, we didn't talk about that yet.
We haven't talked about it yet. We will, though.
Yeah. We're going to talk about it.
Yeah. So the regression equation is my line of best fit.
And StatCrunch gives us that.
Yeah.
Okay.
StatCrunch gives us that.
Okay.
And if I have a significant correlation, then that line is a good predictor.
Oh, so then if I gave you an x value, you could use the equation of the line to predict the y value.
Yes.
Okay.
Yes. If I don't have a significant correlation, then that line of best fit is not a good model.
Then don't use that equation. Don't use that linear equation.
Right. So if I had, a situation where, I thought I had a picture. Sorry.
I thought we had a picture too.
That's okay. I'll just draw one here. So if I had something that was like, say I've got something that looks like that. That does not look like a line, right? That scatter plot does not look like a line. And so if I draw a line that kind of goes through there.
Your line of best fit, that's the line that best fits that data.
Yeah, it's probably still not a very good predictor for like some x value. Okay?
Yeah.
So in that case, right, so say I don't have a significant correlation.
Let's write down. If we fail to reject, then we can't use the line of best fit. So what are we going to do instead?
Equation. We're going to use the mean of the y values as the best prediction of y.
Oh, and that's summary stats. We're just going to do summary stats on the y column and get that mean from the summary stats of the y column.
Yeah.
Okay, and we're going to demonstrate that in a minute.
Yeah.
We'll talk about it.
Yeah.
We keep saying we're going to talk about it.
I know.
Keeps them hanging on.
I know. Hang on. Yeah, but that just means, that line is just kind of meaningless in that case if I failed to reject the null hypothesis.
If you fail to reject, do not use the equation.
Right.
Yes.
Right. Okay, so here is that table of critical values.
Oh, yeah, we told you were going to have to use a table.
Yep. And remember, this is the only time you have to use the table, but you do have to use it.
Yes.
Okay, another thing to note here is that the degrees of freedom, because we have two variable data, is n minus 2.
Right, because we have an x and a y.
Right.
That's happening, all of these are moving parts.
Yeah.
So now you're going to have to make your degrees of freedom n minus 2, and n is the number of points that you're given. It's the number of xy coordinates that you're given, not the number of x's plus the number of y's. It's the number of XY pairs that you're given.
Yeah, so like over here, for example, I've got two columns here. This width is my X and this weight is my Y. We're going to use this data in a second. I have 1, 2, 3, 4, 5, 6. Sorry, I have 6 ordered pairs there.
Okay.
So in this case, I'll just say example, right? N is 6, and so the degrees of freedom would be 4.
Okay.
And so if I were doing this problem, which I'm going to in a second, so I'll go ahead and highlight it, I would be using this row of information.
Okay, because that is where n is 6 and the degrees of freedom is 4. Okay.
Right. And so then depending on my significance level, that will tell me what my critical values are.
Can we circle those 3 headers of significant levels or just kind of do something with them so that we can see? So it's according to what your alpha is, which one of those 3 numbers you choose as your critical value.
Right. And I think in our example, we're gonna have alpha equals 0.05.
Okay.
So then I know by looking at the table that this is gonna be my critical value.
Okay. We'll come back up and get that in a minute. What do you think? What do you say?
Yeah.
Okay.
All right. So, one other thing. This table that's in your notes should be good enough for like most of your homework problems, but it only goes down to n equals 25. There's a longer table on that formula sheet if you want to. If you have,
can we mark that formula sheet? I mean, just kind of just show where it is.
Yeah. So if you click that link, which is also in all of your weekly modules,
every one of them,
there's a link to that. If you need a sample size greater than 25.
Okay.
Or you can look it up on the internet. I mean,
this table's everywhere. It's the Pearson correlation coefficient table. So, yeah.
Oh, there's actually a website also that one of my students found where you can just put in your sample size. It's called mathcracker.com or something like that. Anyway.
We highly recommend you use this table at this point until we've verified MathCracker.
But, you might look for it. Okay.
Sure.
So, using technology, let's look at what these results look like in StatCrunch.
Okay.
Just before we do an actual example here. And I want to go through and highlight what the important information is to get from here, because there's a lot of information in the results.
There are.
Yeah. Okay, so first of all, to find these results, after you put in your X and Y columns, you're going to go to Stat Regression Simple Linear. Okay? All right, all you have to do is select your columns for X and Y variables. And actually, it's really helpful if you rename your columns.
Yeah, we're going to do that, aren't we?
So,
we're going to name it X and Y, aren't we?
Yeah, and I can totally do that.
She can totally do that on the iPad without a keyboard. She's got this.
I got it. I got it. I'm going to name that one X, and I'm going to name this one Y. Okay?
I like that better.
Yeah. Yeah, and what that's going to do is make our equation a little more legible here. Okay, so that's the regression equation. Okay.
Can we write it out so that it can be seen?
Yeah, so this is going to be Y. Oh, sorry. Y equals, and we put a little hat on there because that's a predicted value of Y.
Based on sample data, yeah.
Yeah, and I'm going to round this a little bit, 43.565. So that's my Y-intercept, and then plus 1.315x.
Okay.
And then the other information, here's my R, my correlation coefficient.
Okay.
And so that's my test statistic, right? So my R test statistic is 0.867.
And that's the correlation coefficient for that set of data you've got over there in StatCrunch, right? Okay.
Yep. Well, not for this one.
No, not for that one.
Not
that's
for this
right.
one. No,
don't look at that one.
It's for this set of data, sorry.
Yes. Okay.
Yeah, it's for this set of data over here. And then for the p-value, you always want to look at the slope row, and that's in your notes.
Because there's 2 p-values in the output, and you need to know which one you're using. We are using the slope p-value.
So my p-value there is 0.057.
Okay.
All right, and so we've got that information written down here. Okay. Now, the next question on here is to find the critical values, right?
Oh, we're going to go to the table.
Yeah, so I had 5 data points listed here, right? 1, 2, 3, 4.
Yes, there's 5 data points.
Yes, there's 5 data points. So, let me go back up to the table.
Because it's not the one over there in StatCrunch that you're seeing on your screen. It's the one that we did a picture of that's over on the left. That's it.
Yeah.
This is an example one.
Yeah, and so for this example, I had when alpha equals 0.1, that critical value is 0.805.
Okay.
And when alpha equals 0.01, that critical value is 0.959.
And we have both of those written down there?
Yeah, they're both written down.
And you won't have two alphas. We're doing this because we're going to answer a question based on two different alpha values. That's why you saw two alphas.
Right. So, does this data have a significant linear correlation at alpha equals 0.10? It does have a significant linear correlation because
we're going to show you. Let's do a number line. Can you do a number line?
Mm-hmm. Yeah. Yep. Yeah, so for alpha equals 0.10 or 10% significance level.
Okay. Zero's in the middle, -1 at one end, 1 at the other.
Mm-hmm.
All your R values are between those two.
Yeah. The critical value was...
gosh, I hope you remember it.
-0.805 and positive 0.805.
Okay.
That was our critical value from the table.
Okay.
And our test statistic, remember,
was
that correlation coefficient.
Mm-hmm.
So that would be in the rejection region over here. Okay?
Yep, so we would reject the null.
Exactly.
We have a significant linear correlation.
Mm-hmm. Yeah.
At that level. Let's do the other level.
Yeah, so for the
other alpha.
So for the other alpha, 0.01, I would fail to reject because that correlation coefficient is not going to be in the rejection area.
Okay.
Right? Because if I've got from -1 to 1, the critical values were a lot bigger. They were 0.959. Okay. So that correlation coefficient of 0.867 is not bigger than 0.959. Right?
And it's not in the shaded rejection region. Can we shade those regions real quick? Just to
sure.
Show.
Yeah, so this would be my rejection region here between the critical value and the 1 or -1.
So in one case, we rejected the null because we were in the critical value, but and that was at the 10% level, but at the 1% level, we weren't in the significant level, so we failed to reject.
Yeah.
So at the 10%, we have a good line. At the 1%, we do not.
Right. So it would, it depend on what your significance level and how sure you want to be
that
you have a correlation or not.
Yeah.
Okay, so let's do an example that does use this data that I have over here in StatCrunch.
that Susan's been referring to over and over again, erroneously.
Yeah, that's okay. Now we're actually going to use it.
Okay.
So measuring seals from photos.
Okay.
Okay, listed below are the overhead widths, like taken if you're, flying overhead. In centimeters of seals, measured from photographs and the weights of the seals. The purpose of the study was to determine if weights of seals could be determined from overhead photographs. Construct a scatter plot, and we can look at the scatter plot on StatCrunch and run a regression and correlation test using alpha equals 0.05.
Oh, this is a great application problem because you don't want to weigh every seal.
Right.
But if you can just take what is it, 6 of them?
Yeah.
If you can take 6 seals and fly over, get their width in the picture, and then coordinate that with their weight, actually weigh those 6, then you can figure out whether you can just fly over and look at seals, find their width from your picture, and then estimate their weight without having to weigh the seal.
Right.
This is a good application.
Yep, I like it. Okay, so our claim is that there is a correlation, which means that rho does not equal 0
Right.
I'll check that in the notes and make sure I've got the right symbol there. And our null and alternate hypotheses are always the same. Rho equals 0, there's no correlation, or rho does not equal 0, there is some correlation, is the alternate hypothesis.
Okay.
Okay. So we found on that table that the critical values...
Oh, yeah, back up when we looked at the table, we saw that at the 0.05 level.
Because n equals 6, and our alpha was 0.05. Okay. So we found that those critical values are 0.811, okay, which makes my rejection area between 0.811 and 1. Oh,
or whatever.
I don't know what that means.
We don't know what that is, and we don't know how to make it. I think you have to slide it down. Yep.
Okay. All right. Sorry about that.
We don't know what that happened.
And then the negative one be negative 0.811. Okay. Well, my correlation coefficient is going to be positive, but let's look at that in StatCrunch. We'll go through finding that information in StatCrunch.
Yeah, we'll show you how to do it.
Okay. All right. So let me move over here. So I've got my data in here. I've got the X column is the overhead width, and the Y column is the weight.
Okay.
And I'm going to go to Stat, Regression, Simple Linear. Okay. We're not going to do any other types of correlation and regression. We're only going to do simple linear in this course. Okay. So I'm going to pick my X column. I'm going to pick my Y column. And then I just hit compute. And that's all I need to do. Okay.
Okay.
So, this is where I got my correlation coefficient here, right? And then I'm going to also look at the equation, which is up here, and my p-value, which is the 0.0039.
Okay.
But let's take a look at the scatter plot.
Oh, yeah. Ooh, that's a pretty good line, actually.
Yeah, that's a pretty good fit.
Pretty good fit.
For only having, 6 points, it's pretty good. So, all right. So let's, put that information back over here. My question. So my test statistic, my correlation coefficient R, it looks like that is definitely more than my critical value, right?
Yeah.
So that was 0.9485. Was my R test statistic.
Okay. Which is the correlation coefficient for those points that we saw just a minute ago. Yeah.
And then also my p-value, 0.0039, that is definitely less than alpha, which is 0.05. Okay. So I'm going to reject the null hypothesis here, right?
Right.
Okay. So that means that there is sufficient evidence to support a claim of linear correlation.
Time for Christina to go to class.
Good. So, since I rejected the null hypothesis, my equation, which was over there in my results, I've rounded it a little bit here.
Okay.
But that is a good predictor.
Yeah, so we can use it. So now, if we're asked an X value, then we could possibly use that.
Right.
To calculate. So if we were asked a width of a seal, we could possibly use it to calculate the weight of the seal.
Right.
Okay.
Right. So this says find the best predicted weight of the seal if the overhead width measurement is 9 centimeters.
Okay.
So I would take that 9 centimeters and put it in for the X in my equation.
And then just work it out on your calculator.
Exactly.
And get the answer. And what was our answer?
204.8 kilograms.
Okay.
Yep.
We have 2 more things we need to cover. This last question, and then we need to talk about what would happen if we failed to reject.
Right.
Okay?
Right. So the last question here, could the regression equation be used to predict the weight of a seal with a width measurement of 3.1 centimeters?
You know what? Let's look back at that data just a second.
Yeah.
And when we look at that, 3.1 is not in that domain of X's that we've got there.
Yeah, it's actually significantly different. Like, I would feel comfortable using that line to predict something like a width of maybe 6.9
Yeah.
or like 7.
Yeah.
But 3 is like significantly different than our data.
Right, because that's like a baby seal.
Right.
And a baby seal may not have the same proportions, as an adult.
Yeah.
So just because you measure the width of it on the picture doesn't mean you can guess the weight or you can calculate the weight of it.
Yeah.
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 So I'd say no. I don't think we can use that line to predict the weight of a seal that has 3.1 centimeter width.
I don't think so either. Okay.
Okay, now last thing. If we had, just because we want to show you what would happen, if you failed to reject, we did not fail to reject, but if you did fail to reject, you can't use that equation to answer the question about, what was it,
9 centimeter.
9 centimeter. Yeah. So you've got to find another way to answer that question, and here's what you're going to do.
So I would go to, what I want to find is the average of the y values.
Yes.
Because that would be my best prediction. So I would just go to stat. Remember, we did this way back in Unit 1.
Summary stats. Hello, summary stats.
Summary stats columns, and I could just find the summary stats for my y column.
Where's the button to push?
I don't know. That's a good question. All right, there we go.
Okay.
And then, so then I would want to use that mean of 184.67.
So that's the mean of all of the y values. So basically, if somebody asked you 9, you'd say 184.
Right.
And then if somebody asked you 7.5, you'd say 184.
Yeah.
And whatever they asked that was a legitimate, in the values that we started with, something not like a 3.
No.
We wouldn't say it for that. But for anything that's a legit question about X, we're just going to say 184.
Yep.
So that's what you do if you fail to reject. Just answer the mean of the y values.
Right. And remember, that's up here in your notes. So just don't skip over the words. That is, if you fail to reject, use the average of the y values.
Yep.
Okay. Good. All right.
Last thing, we have one more question that we're not going to work, but we want you to work.
Yeah. So work this, and then check your work using the answer key. Okay. And we'll see you next time.
Okay.